Hello everyone. I'm putting together a short video of some testing and estimation exercises from our lesson 3 exercises. But I've made a new data set that has 3 of the problems from our exercises. But I added in an Anova problem and a chi-square problem as well. So let's take a look at some of these exercises. So the first one is about a portfolio underperforming its target. So an investor has a portfolio, and the promise made to the investor was that the portfolio would have about the same return as the stock market overall. So the S&P 500 was used as a benchmark. So we're going to test the portfolio's performance against the benchmark to see if in fact the portfolio underperformed. So that would be variable 1 and a 1 sample t. Now, over the 39 months, the portfolio had an average monthly return of negative 1.1, which makes our standard error about 0.96%. Our null hypothesis would be that benchmark value. So over the same 39 months, the S&P 500 had a return of positive 0.95. So we can see right away that the mean for the portfolio over those 39 months is 2.137 standard errors below 0.95. On our t-curve for 38 degrees of freedom n minus 1, the p-value is 0.0391. And we're running this as a two-tailed test to be fair, right? So we're not looking for one thing like underperformance. We're setting it up with a pretty high standard using that two-sided or two-tailed p-value. But even using that higher standard, our p-value is less than 5% alpha. So our null hypothesis is rejected. So here we can see that the portfolio did in fact underperform its benchmark. We have a 95% confidence interval showing the estimate. So if the market stayed the same and the portfolio stayed the same, we're 95% confident that the long run mean monthly return would be somewhere between a loss of 3% up to positive 0.84%. Now we can also estimate how different the portfolio is from that benchmark simply by comparing it directly against the benchmark. And our upper limit. So this is essentially the same confidence interval, but it is in comparison to the benchmark. So here we could say that we're 95% confident that the portfolio could differ from the S&P by as much as 3.99% less and up to 0.11% less. So clearly the portfolio differs from the S&P, and the amount of difference in this case was used to award damages to the investor through an independent arbitration panel. All right, let's try another one. The second one is a match samples t-test, French language instruction. So we have a couple of variables here about the effectiveness of a executive French language program. So this is done in international business quite a lot, where conversational French, related to the business operation or the business meeting that has to take place, or other useful things for interacting in an international setting. So that kind of program is what we're considering. But these programs, there are many alternatives, right? We can use many different commercial programs and get the same thing. So they want to see, is our executive training program in French language worth it? Should we keep it? Does it actually work? Is it worth the expense at our company? So this would be a match samples T, and the two variables here are pre and post test scores. So everybody there, maybe some have some French background, maybe some have less, right? So we're going to compare their starting score to their ending score in order to assess the effectiveness of the program. So the post-test is variable 2, and the pre-test is variable 3. So now we're seeking that information about gains. We're looking at the post-test minus the pre-test to calculate our differences for our match sample T. So our post-test minus our pre-test gives us our differences, and these are going to be the data for our one sample T. So the match samples T reduces to that same one sample T once we get our differences. So our 20 executives had an average gain from pre-test to post-test of 2.5, making our standard error here 0.6469. The null hypothesis for the match samples T for us is always that mu D equals 0. So here we're assuming no effect of the training program, no change from pre to post test. And so simply we're considering, is 2.5 enough to be statistically significant? And here the answer is yes. And not just yes, a little, it's highly significant. So T for 19 degrees of freedom is 3.86. And that makes our two-tailed p-value very close to 0, 0.0010. So this is not only significant at the 5% alpha level, but it's also what we call a highly significant result with a p-value less than 1% alpha. In fact, if we change our confidence interval up to 99%, you can see that we still are able to exclude that UD test value of 0. Okay, so is the program worth it? Well, what we know is that we have a highly significant result statistically. And looking at our 95% confidence interval, we see that the average gain from pre to post test is somewhere in the range 1.15 to 3.85 points. Now, one piece of information that we would lack in order to really know if the program works is how many points on the test, right? If our upper limit on gains is 3.85 points, well, if there's 100 points, that would not be really a lot of change, right? But we have our data, and it just looking at the scores, we can see that there's probably maybe 36. That's our high score here. Here's another 36, right? We don't have anything over that. We have a lot under that. So we're going to guess that the upper limit is probably about 10% gain from pre to post And that gives us a better idea of the practical effectiveness. But statistically speaking, we are quite sure that at least the scores will go up. In other words, the program fundamentally works. We could then just be a little bit selective about the amount of the effect, looking at that confidence interval. So is this amount of change worth it to us? We know we're going to get it because the result is so strong, but is that amount worth it to us? That's still something that we could discuss or debate. Let's try another one. So number 3 is a 2-sample t-test that I like a lot. This is from some real data on gender and the SSHA scores. So SSHA, Survey of Study Habits and Attitudes. So we have data on the gender of the respondent and the score that they made on the SSHA. So we're trying to consider whether there's some relationship between the respondent's gender and their score. So this one, our data are in columns 4 and 5. 4 and 5. And this one, of course, would be a 2-sample T because we're comparing two groups of a quantitative variable. So we're grouping the score, variable 5, into two categories, men and women. Our 2-sample t-test will take those data and group them and obtain what we call our observed difference. Okay, so looking at our results, our 18 women have an average score really close to 143, 142.944, and our 20 men have an average score of 122.5. So the women outscored the men on average 20.44 points. Is that enough to be statistically significant? Well, to test that, we're going to assume that the men and women in the entire population have exactly the same mean. So the difference between them is 0. In other words, we're assuming that gender has 0 effect on the score. Then we can simply test 20.44 relative to that 0 test value. And we find that 20.44 is actually 2.22 standard errors above 0, which produces a p-value, two-tailed p-value of 0.0328. Remember, our degrees of freedom for the 2-sample t are determined by the spreadsheet or any statistical software that we use. And this is the Satterthwaite approximation of degrees of freedom. So using that t-curve for 35 degrees of freedom, we would say t for 35 degrees of freedom is 2.22, p equals 0.0328, which is less than 0.05. So here we can reject the null of equal means. Now, what would we conclude? Well, I'm going to conclude that the women on average have a higher score. Now the question is, how much higher? Remember, we could have a significant effect statistically, but it might be, in terms of effect size, a very small effect. Just like we saw in the previous example, highly significant result, but then we wanted to look at how much change are we really getting in a practical sense. So here the 95% confidence interval shows that the women on average score 1.775 to all the way up to 39.113 points higher than the men on average. Okay, so this is quite a significant change, but it could be rather small in amount. right? Once we factor in that rather large margin of error, you see, 20.44 is the observed change, but when we calculate the right margin of error for this case, it's all the way up to 18.67. So that means nearly all of that 20.44 can go away, right? Randomly. We don't know. That's why it's a margin of error. Now, why is the margin of error so big? Well, the margin of error is so big because of the standard deviations in our samples, but mostly because our sample size is relatively small. Now, in a case where the sample size is relatively small, it's particularly important for us to check our sample data for anything unusual, like outliers that might affect our results. So let's use our group mean analysis to get some visibility. This is our grouping tool to get some visibility on the two samples of scores, right? So we're going to now filter, or group in other words, by women. And so there's no clear outliers according to the z-scores. There is a little mild skew to the right. That's because the women have a perfect score of 200 in their group. And that perfect score is not a clear outlier, but it's certainly pushing up the mean and adding variability, right? So that's going to pull the mean for the women up a little bit. It's also going to make our standard error for the two sample t-test a little higher, right? So it's definitely contributing to the result. Let's look at the men. Okay, so they have a sample mean of 122, not a pretty close to a normal distribution here, as a matter of fact. So we have just a little bit of skew to the right, but remember, a little bit of skew is like saying approximately normal. So here we have an approximately normal distribution. Let's take a closer look at our z-scores. So here for the men, we have a score of 187 is our max, and that has a z-score of 2. Let's see if there's any low z-scores. We have a score of 75 for the men, right? So that has the, looks like the largest negative z-score. Here's another one at 70 with a negative z of 1.63. So a couple of low scores in a relatively small sample of men, and nowhere close to that minimum for the women, although the max for the men is relatively close to the max for the women. But we can see why our two sample t-test is producing the result that it is. We have a couple of low scores in our sample, right? Without those really low scores in the sample for men, the result might not even be statistically significant, right? But no clear outliers, no strong skew, nothing that would make it wrong to use this test and these results, but we recognize a limitation in this test, right? We see the high margin of error and we see the relatively small samples, so we understand why we're getting the result, and that might temper our use of this result. But certainly an interesting finding in any event. Let's try another one. This one's an Anova, and this one is based on the original L3 exercise on the machine capacity. But here we have an additional variable, the type of operation. So an engineering team is testing 3 types of operation of a recycling plant. So they're trying to improve the performance, trying to optimize the performance of the plant. So they're looking at 3 different types of operation and trying to test each one to see if there's a significant difference between them, which one's the best, which one's the worst. We can learn all of that from our Anova. So our capacity in pounds per hour is going to be our dependent variable. And then type A, B, and C will of course be our independent variable. So A, B, and C. And our capacity variable number 6. So this is going to be our Anova. Okay, so our independent variable has 3 categories, and our dependent variable is quantitative. This is when we use Anova. IV in categories, and we need 3. And the DV is quantitative. Now, of course, we can use Anova with many more than 3 categories, but for us, we're either looking at 2 sample T, or 3 Anova. All right, so here our F ratio is 47.895. So we would say that F for 2,87 degrees of freedom equals 47.895. P equals 0.0000, and that P is less than 1% alpha. You can see that the critical F, right, F critical or F star is 4.858 at the 1% alpha. Remember that F curve, that F distribution is always skewed to the right. So the larger F is, all else being equal, the lower the p-value will be. So as F increases, the result is it's showing us that the result is stronger. Stronger results are clearer results. So we know for sure that there is a significant difference in the mean amount per hour for these 3 types of operation. So let's look at our post hoc analysis to learn more about the specific differences. So our group confidence intervals for A, B, and C. So we can see that there is a little bit of common range, actually a fair amount of common range between A and B. So there's a little bit of difference between the means, but when we factor in the margin of error, we can see there's a lot of common range. So 37.8 to 44.7 and 34.5 up to 40.7. So the upper limit on A is better, but they have a lot of range in common, so we can't really say that one is clearly better. We can't say that A is always going to be better than B, but it does have a higher upper limit. That's what we can see from those two. Now C, we can see, is totally different, and this is why our p-value is 0, because C has only a range that goes up to 26,227, right? So the type of operation, type C, is a lot worse than A and B. A and B are similar. If I had to pick one over the other, why not go with A? Unless B is a lot cheaper, then definitely go with B, because A and B are going to perform pretty comparably. Now, in the same way we did for our 2 sample T, we need to check our data using our descriptive statistics tool. Now, before we do that, let's look right here at our summary statistics for each group. Remember, when we use Anova, we're assuming that each group has a normal distribution, just like T. But for Anova, there's something additional. We are assuming also equal variance for each group. And we check that by looking at the sample standard deviations. So here we can see that C has a standard deviation way up at 11,271. The smallest standard deviation is B at only 5,167. So this would not pass our 2 times rule. 2 times the 5,167 is less than our max standard deviation. So C is quite different in its distribution than A and B. So our Anova is highly significant, but we fail that 2 times rule, which would make our result here quite unreliable. See, what we're looking at is we're saying that C is probably such an entirely different population of data that of course we would assume that there would be a big difference in the mean because it's an entirely different distribution, an entirely different population. So when the standard deviations are this much have this much difference, we would expect there to be also a big difference in the means because this is just a totally different population. So let's look at that on our descriptive statistics to see why, if we can detect why that is happening in our data. So we're going to change our quantitative variable to number 6, and our grouping variable is going to be those types, variable 7. So A has an outlier. So the A, remember, had the highest range. So maybe A and B are actually closer than we even thought looking at our confidence intervals. On our confidence intervals, we said there's a little bit of common range there between A and B. Well, A was a little bit higher for the upper limit, but it has that high outlier kind of pulling things up, right? Kind of adding that positive skew. Let's look at B. Well, B has that same outlier, right? So those would tend to offset in our judgment. So they each have one outlier, and both of those are greater than C. So the outliers could be contributing to the amount of difference that we see between A and B as compared to C, though the samples are relatively large here and the effect would be minimal in terms of the outlier. Let's look at C. C is the one where we have some issues, it looks like, with our data, but there doesn't appear to be any outliers. Here's our data, though, and we can see that although these last 3 z-scores are not clearly outliers, let's look at the data itself. The data itself, 1500, 2500, 2000, these don't even look like the other measurements. Not only are they so much less than the other measurements, but they're just not the same type of data, right? We have in these nice round numbers, 1500, 2500, 2000. This is probably just an error in our data or something like that. So not a clear outlier, but if we look carefully, we can still see that, wow, there's these 3 values that don't really make a lot of sense in our data. And let's go back to our testing tool and remove those. Let's see if at least we can, because removing those low values is going to at least change our standard deviation. First, it's going to make the mean greater, but it's going to also make the standard deviation less. Now, we would only be able to do this if there was a good reason, such as the data appear to be clearly wrong, right? So there's something wrong with these data. So we're going to get rid of those. and recheck our results. So we succeeded, right? So we still have the same effect, okay? A and B are both significantly greater than C. But our standard deviation without those bad data is within the 2 times limit. And our Anova result did not change substantially. It's still a highly significant Anova result. Let's look at one more. The wine and music example. This is a chi-square test of independence. And it's a very interesting use of the chi-square test of independence. We're looking at the relationship between the music playing in a wine store and the purchases of wine made while that music is being played. So we have 3 music categories and 3 wine categories. So our 3 by 3 crosstab is going to be the basis for our chi-square test of independence. So our chi-square is going to be based on the music as the independent variable and the wine selected as the dependent variable. So can the music playing, variable number 9, have an effect on the purchase? So sometimes there was no music playing. That's a pretty good control. Sometimes there was Italian music playing, and sometimes there was French music playing. So we're testing these 3 categories, none, Italian, and French, against the wine that was selected. So there could be other types of wine selected, or Italian, or French. So here's our 3 by 3, right? So our independent variable is categorical, our dependent variable is categorical. That's a job for our chi-square test of independence. Okay, so we have n equals 243 total purchases. But really, what we're looking at here are 3 groups, or really, we could think of this as 3 samples. We have one sample when no music is playing. So 84 purchases were made when the music was off. And when the music is off, 43 of those 84, right? So more than half of the purchases are just something other than Italian or French wine. Always selling, it looks like a rather large percentage of the wine is French, but a large percentage of wine is French. And we can see that 11 out of 84 of the purchases were Italian wines with no music playing. When the music changes to Italian, right? So we have another sample of 84 purchases when Italian music is playing. So the other wine rate drops. It goes from 43 down to 35. Now, where do those 8 go? They go into the Italian wine purchase. French holds constant at 30. All right, so the French music, 35, well, we have, first of all, 75 purchases when the French music is playing, and we could see the effect is strongest here. When French music is playing, the sales of Italian wine really drop. Still holding pretty constant here in the other category. That seems to be pretty independent of the music. But the effects that we note here are when the Italian music is playing, we sell more Italian wine. When the French music is playing, we sell more French wine. Let's look at that in our post hoc analysis. So we already know that we're going to reject the null of no association. The question is why? And that's not a statement of the result. We can see that the chi-square for 4 degrees of freedom is 18.28 and the p-value is 0.0011. So there's actually a highly significant association between the music and the purchase that's made. But what is that association? So we kind of talked through that already looking at the crosstab, but our conditional distribution and our clustered bar graph might make that even clearer. So when there's no music playing, we can see that the other types of wines sell, regardless of the music playing, none, Italian or French, we can see that these bars and percentages are roughly the same. No strong effects there. But when the Italian music is playing, right, we can see that we do see some changes, right? The Italian category jumps up and the French category down. And we see the reverse effect when the French music is playing. So our result is statistically significant overall. We reject the null, but of course we need, for chi-square, like with Anova, we need that post hoc analysis to get to those specific effects. So this is a look through some L3 exercises, and I'll add this video to our lesson as well as the Word document.